Hi everyone, thanks for attending my presentation. I'm Hsu-Chieh. This is a joint work with my advisor Stephen Smith. The title of this work is Learning Model Parameters for Decentralized Schedule-Driven Traffic Control. Traffic congestion is a serious problem now, and it's cost United States cities over 160 billion every year in time and fuel. And if you drive your car, you probably spend more than 40% of your time on street idling. There are two main reasons. And the first one is that our traffic signal is only optimized for average traffic condition instead of making real-time decisions. And the second one is the way we use sensor is only for detecting stopped vehicles. Generally speaking, our intersections are not smart enough. Schedule-driven traffic control is a new real-time approach that we propose to solve this problem, in which we have three different components. The first one is cluster representation. We cluster vehicles based on their distance. After that, we will have a sequence of clusters. And by solving a single machine scheduling problem, we can generate the schedule every second. And then this intersection can communicate the schedule to the downstream intersection as a prediction. And the downstream intersection will combine its local detected clusters with the received non-local clusters. This whole process will repeat every second and happen at every intersection. Schedule-driven traffic control is a model-based intersection optimization method. That means we rely on a model and setting parameters, and we assume the control model is sufficiently accurate to represent the real problem. By using our modeling and the parameters, the space is defined and searched through optimization process. From our past experiences, we found that different parameters are actually suitable for different traffic patterns. So now the question is, can we combine planning with learning, especially reinforced learning, to configure parameters? Our solution to this problem is we create a new additional learning layer on top of the scheduler. And this layer is responsible for a larger time scale. By applying the reinforced learning framework, we can configure the parameters adaptively. So we use the cluster representation as our observation of the state, the major delay as our negative reward, and the parameter as our actions. And the scheduler can still generate a schedule at a smaller time scale. So by using this hierarchical structure, we can solve this problem. And in this work, we focus on mixed migrant time as our parameters, which is used to constrain the phase duration length. And we use it as a starting point for this line of research. And the algorithm we apply here is called the actor-critic algorithm. We learn both policy and the value function at the same time for multi-agent environment. And we use the actor network to represent the policy function and use the critic network to represent the value function. So we can write down the policy gradient in this form. However, the max migrant time is a continuous value. So we replace the stochastic policy with the deterministic policy here. So the entire policy gradient can be rewritten in this new form. Given a transportation queuing network, we assume that each intersection has their own policy to configure their corresponding parameters. So the gradient of their policy can be computed given the global state and the Q function. Due to the structure of the traffic control problem, this Q function can be decomposed into a summation of link-based Q function, which is a function of global state and the neighbor actions. So after plugging this relationship into our formula of policy gradient, we found that each intersection can compute its gradient locally if we have the neighbor action and the global state. So now we want to define the state, actions, and the laws for each intersection. As mentioned previously, schedule-driven traffic control applies replanning every second to generate the schedule. So we can get the queue length for different phases and the number of approaching vehicles from different directions. And we also can take average the queue length and the number of approaching vehicle over a period of time. So we use that as our features of state. And we take the maximum green time as our actions. And the average delay over neighbors and the period of time t as our negative reward. So we already showed that given the global state and the neighbor actions, we can each intersection can compute its gradient locally. However, our schedule-driven traffic control is a fully decentralized system. We're just wondering, can we relax the requirement of knowing the global state a little bit? So here we provide an approximation of this global state. So here's example. We assume that this intersection I knows the average queue length from the different 4 different neighbors, and also know its number of approaching vehicle from also these 4 neighbors. So we just propose that we want to use this average queue length and the average number of approaching vehicle as approximation of the global state for intersection I. So by using this approximation, we can rewrite the Q function for in this new form. So we just need to record this transition and put this transition into the replay buffer, and we can use that to update the actor and the credit network. So here in this table, we show that the continuous action is outperforming the discrete actions, in which we only have a finite number of maximum green time to select, and also outperform the fixed maximum green time. And here we show that the hierarchical algorithm is actually better than the original schedule-driven traffic control and the cycle-based adaptive systems. Here, we want to emphasize that the learning process is an episodic reinforced learning for avoiding the terminal state that the queue instability cannot retain. And we show that our proposed algorithm outperform the other 2 approaches on the different demand, and also a realistic PM rush hour. And the learning performance is also show a decreasing trend. And here we also visualize the policy here. You can see that there's a nonlinear relationship for for the policy function. So now comes to the conclusion. The first one is self-improving to stabilize the network is realized through learning to configure parameters of the model, and real-time responsiveness is still retained. And the hierarchical abstraction retains both advantages from learning and planning. And also we show that sharing real-time information to the neighbors can enable a decentralized multi-agent learning. Our future work will be how to cope with the non-stationary traffic. Thank you.